We are discussing a top down design example. Just to illustrate the concept, we took a simple design wherein a register is loaded with the data, and we will count the number of ones in that register, the data, and put that value, the number of ones, in another register and stop the operation. So, this is a simple system. We talked about the functional unit requirements. We need two registers, register A and register. This is the partitioning between functional units and control units. Data goes into the functional unit and data goes out of the functional unit, but the functional units are controlled by command signals. The output of the functional unit, the conditions of the outputs of the functional units are given back as status information to the control unit, which helps the control unit to steer it from state to state. In addition, the control units can have external inputs and external outputs. External inputs meaning things like start, reset and stuff like that. And external outputs could be typically the status, what is the operation over, complete, or some other problem, error message, whatever you want to display as control outputs. And this is the functional units. People also call this functional units architecture of the problem. I was avoiding this term, but I thought it's better to give it to you. Architecture is what is the concept of all this together. Architecture is the combination of the functional units. The group of functional units is called architecture. So, the architecture consists of two registers. The architecture is controlled by the control unit. So, the partitioning of the control unit and functional units, some people call this functional units part as an architecture part. Architecture is the one which processes the data, control unit is the one which controls the operation of the architecture. So, I use the word functional units because it is more sort of clear to understand, easy to understand. Anyway, the architecture of the functional units, whatever way we want to call it, in this particular problem consists of two registers. The register A, which is into which we will load the data. Since we do not know how many bits, we are going to put an n bit register, and it should be a parallel in, so that we can load the data, and parallel out if we want to take it out. And then we want to load it. When we are ready to put the data into the register, we need to load it. So, there is a load signal required. All of them are controlled by clock, system clock. So, there will be a clock. And then one feature, the algorithm we are going to do is, there are several ways in which you can do this problem. One of the ways is to look at the LSB, the least significant bit of the word, and see if it is a 1 or a 0. So, 1, add 1 to the register B, otherwise go and shift it and look at the you always look at the LSB by shifting it till you exhaust all the bits. So, we need a shift register with a shift right feature. A shift right feature, a loading feature, a clock, data in and data out. These are the specifications or the requirements of the register A. As I said earlier, you are supposed to have a component which is available either commercially or with you in your earlier design as a code or a IP, they call it. IP stands for intellectual property. That is, you develop even in an IC design, even though you build from gates, supposing you have a particular complexity, some subsystem of a particular complexity, that subsystem can be repeatedly used by you. It is your property, which you will use again and again. If somebody else wants to use that, he has to pay a royalty to you for that. So, such a thing is called an IP in this industry, the industry of design industry. IP stands for intellectual property. That is, you have developed a functional unit from basics, and that functional unit is available as a code to be integrated into the software the other person is developing for his application. Anyway, it is available as a component. We are talking about discrete components in this series of lectures. So, we will call it a register which is off the shelf components available in the market, commercial. A register B is the one in which we will store the value of the number of ones. So, the number of ones will be maximum number of ones will be all ones for n bits. So, n. So, that will be logarithm to base logarithm the logarithm of n to base 2, and it has to be plus 1, and this will be a counter which will be initially cleared, and then the clock will go, but then the clock will not count it up, it will count up only by a count enabled signal. The clock is common to all the registers, the system clock. Having decided this architecture of the functional blocks, we will go to the state graph of the control unit. It is a very simple state graph. It stays in a state called S0. It is a reset state. I can have a notes here somewhere. S0 is reset state. I am going to assume a signal called S, the start signal is going to come. Only when this S comes, you start loading the register A and then start counting the register B, counting the number of ones and putting the value in the register B. So, I am going to assume a signal called start signal. If the start signal is 0, I continue in this state. So, S is start signal. If S is 1, I go to the next state, I will call this state S1. But before doing that, when as soon as S is 1, I would like to clear the register B and load my value, the bits into the register A. So, S is equal to 1 will give an output of load A, clear B. These are outputs. Load A, clear B are the outputs when S is equal to 1 in state S0. In S is equal to 0, when S is 0, it continues to be there. When S is equal to 1, it goes to the next state with giving these two outputs. Okay. In S is equal to 1, see, suppose they are all zeros. How do you know we have finished the job? I keep shifting the number of bits. I keep shifting the register A and filling the shifted positions with zeros. When all the bits are 0, I have to stop the operation. That means the value of the register A is 0, I end the operation. Or it may be that I am loading all zeros, then also it need not do the operation. So, when the value of the register A is 0, I want to terminate the operation. So, I am going to call a signal A. Signal A is a signal which will become 1 when the value of the register is 0. So, it is a signal I am defining. All these things I should account for in the architecture, the functional units. So, A is a signal which gives you the content of register A is 0. Register 0. So, if A is 1, that means I have either completed the operation or there is nothing to count, either way. Why I put the same value? A is the register, A is the value of the register A. So, that register, then in that case I go to S2 state. So, I am ready to go to reset and load the next value, but S is a signal which is start signal. It could be a manual signal. Somebody pushed a button. If I do not make sure that S is 0 again, I may go back and redo the same thing. Supposing I have a non-zero value of A and it is going to take just a few clock cycles to count number of ones. Still, if S is not released from your, you not release the S, the start signal. You make a start signal 1 and you have started the work and you completed the work and S is still 1, I will go back and again it will redo the same thing over again. I do not want to do that. So, before going back, I will have to make sure that the S has been removed completely to 0, and then the next time it comes 1, again it will start the operation. Something like you want to let one person in into the room, you open the gate and then you keep it open sufficient long so a lot of people can enter. How do you control it? So, make sure that you close it and open it again. Only time, every time the door opens, only you can leave the person in. You can make a algorithm or instruction, given instruction. Just because the door is open, you should not come in. Only when the door is shut and then it is open, you should come in. Something like that. So, what I am trying to say is, if after doing this I find I is equal to 1, either because the value you have loaded is 0 to start with, or you have finished the job, either case I am done, I am ready to start the next operation, next count, next loading of next value to register A and counting it again. All of that, before I remove doing that, I should once remove the start signal and then get the start signal one more time. Every time a start signal comes, I should do the operation only once. When there is a start signal, I load, finish count, stop. Again, next time the start signal comes, I again load next value. Otherwise, I will be doing the same thing again and again. I will be counting the number of ones in the same value repeatedly. There is no point in doing it. So, what do I do for that is, I will now see whether S is 1. If S is 1, I will not go out of this loop. That means I have not removed this signal S is equal to 1, because I did not say S is equal to 1 is going to last for only clock period, 1 clock period. If I said it is only for 1 clock period, then I will be safe. But I do not know what is the duration of this S signal. It is a manual push. It can last for several clock cycles. By the time you can finish the operation, still S is equal to 1. So, you do not want to go back, right. So, if S is equal to 0, I will go back. So, that part is over. Now, the counting part remains. So, how am I going to count? I am going to look at the LSB. So, I am going to see if A is equal to 1, that means the value of A is, the register is 0. A is equal to 1 means value 0. Register A is 0 is called A. So, A is 0, that means A is not 1, that means A is 0. Then I have two choices. I have the bit looking at the LSB is 0 or 1. If 0, I do not count, but I shift. If it is 1, I shift and count. So, I have two possibilities. So, A is equal to 0 is a non-zero value of the register A, and my last bit I am going to call it A0 is equal to 0, last bit 0. LSB, A0 is the LSB of the register A. Non-zero value and LSB 0, I do not count, I shift. So, I go to the state S3, and in S3 I issue a command of what? Shift A, I shift A. So, this signal is shift signal. And then go back and see if A is going to become 1. On the other hand, if A is 0 and A0 is also 1, I should count 1, B has to be incremented by 1, then I shift and then I go back. So, I have to A0 is 1, LSB is 1, I will go to another state called S4, and here I will say count. and then I go here and then I go here. I have not drawn it very neatly, I know, but I have developed it. You can redo it and then look like what you see in books. That is not the point. The point is to know how to do it properly. Now, let me go over the whole algorithm one more time quickly. We are waiting for a signal called start. When it is not there, we keep in that reset state, we keep the system in the reset state, and we find that S is equal to 1 suddenly. And then before you go to the state S1 where they start the operation, before doing so you have to load the register A with the value that you want, for which you want to count the number of ones, and you have to clear B because you have to start with the 0 count. And then you find the value of A. If it's 0, there is nothing to count, you have to stop. But before doing so, I can directly go back and wait for the next start, but I do not know whether the earlier start has been removed. So, in order to do that, I am introducing an extra state called S2, in which I will wait if S continues to be 1. When S becomes 0, I return. After loading S1 A, I find if it is a non-zero value, I have to look at A0. If A0 is 0, non-zero value, if A0 is 0, I do not do anything but simply shift it by 1 position to the right. So, a non-zero value and LSB 0, I shift it and then look at this, again look at the value. If it is 0, I will continue, otherwise go back this loop. On the other hand, the non-zero value and the first bit is 1, A0 is 1, LSB is 1. Then I do this operation, shifting has to be done, verification has to be done, but before all that I have to count up by 1. Any questions here? Is it a Moore machine or a Mealy machine? The combination. So, there is nothing like a Moore machine or Mealy machine, because these two are Moore outputs, this is a Mealy output, is it not? So, systems need not be Moore or Mealy, right. So, what are the outputs now? Count, we have already defined this, count enable, B, shift right A, shift right A, load A, clear B. Two other inputs we are not taken into account. We are required here. I am monitoring A is equal to 0. The value of the register, it has to come from the functional unit. That means, remember I said we have to go back and forth between architecture and the functional units and the ASM. As I draw the state graph, I will find out the limitations of my functional units, inadequacy of my functional units, and come back. Now, what I have not done is, how are you going to verify whether A is equal to 0 or 1? I have not thought of it till now. I did not know it was required when I was drawing this, but now I am drawing this circuit. I know when I draw the state graph, I know there is a need for it. It is a need for it. So, how am I going to do that? It is very easy, because I have the output data. I put a register gate here to find out if it is 0 or 1, isn't it? So, I will have to now give this out of this. So, I will have, if all the bits are 1, how do you know if it is a 1 or a 0? What gate will give you? NOR gate can give you, anything can give you actually, depending on how you connect it. Supposing I give you a NOR gate, if it is 1, if everything is 0, this will be 1. So, that is what we want. A is equal to 1 is all of 0. This extra functional unit requirement was not evident at the time of drawing the architecture part of the functional unit part. Only when I went to the state graph I remembered, or I not remembered, I found out that something like that is required, and at least the way in which I am doing this problem. Of course, you can do it some other way, more efficient, fine. Other thing is, I want to know A0, that is easy, because I have all these bits here. All the 8 bits are available here, 8 bits or n bits are available, all I have to look at the LSB. So, LSB is only here. So, A0 is here. So, both of these things come from here. So, the two extra inputs which we did not think of in this case are the LSB of the word and the 0 value. 0 value is called A is equal to 1 means register A's value is 0, A0 is the LSB, that is because all the bits are available, the least significant bit you take and put it. So, these are the outputs of the what? Of the control units. Inputs of the control unit are what? Yes, start switch, is not it? It is an input to the control unit. A, value of A and A0. Anything else? No. So, now rest of the problem is simple. I have a state graph, inputs output clearly defined, present state, next state, draw ROM implementation, PL implementation, MUX implementation, whatever implementation you can imagine. Do you understand what I am saying? So, the most important problem is to understand it, partition it to the extent possible of what is available already off the shelf or the as a previously designed functional unit with you or a subsystem with you. Identify the input output signals of this unit and see whether they can be used in the controller. Start drawing the state graph, control the functional units in the sequence required to realize the specifications. Go back and forth couple of times, iterate between these two to find out all the signals are accounted for, all the signals are required as control unit inputs are accounted for in the architecture, and all the functional outputs required from all the functional outputs coming out of the controller can be accommodated into the functional unit, so that they can realize what is required, they can implement what is required. Then when you are done and you are satisfied with and the algorithms also should be right. Do not worry only with signals, and then finally if it is not doing what it was required to do, then it is no good. So, then you have the state graph, and I am not going to implement it, you have done it hundreds of times at least, if I assume that you are doing some of these exercises at home. So, what I am going to do is to simply write the state table and leave you to do the rest of the work. State table would be present state, call it, we will have the standard nomenclature. S0 is 0 0 0, S1 is 0 0 1, S2 is 0 1 0, S3 is 0 1 1, S4 is 1 0 0, okay? And let us call this XYZ, where I am using AB too many times. So, present state XYZ, input conditions, next state, X Z, outputs. Outputs are load A, clear B, shift A, count B. So, present state 0 0 0, S0, S is equal to condition S bar remains here, yes, here no outputs, here output 1 1. Present state 0 0 0, if start signal is not there, remain in the same state without any output. If S is equal to 1, go to the next state 0 0 1 state, and give the outputs load A and clear B, and then S1 0 0 1. 3 possibilities are there. I will just simply write it A bar, one one 1 0 0. No outputs, no outputs in any of these. So please tell me if I made a mistake in drawing it when I write this table fast. Then 0 1 0 S bar, again yes, remains in no outputs. 0 1 0, it goes to 0 0 0, again no output. One 0 1 1, zero 1 1 without anything. Huh? Which one? 0? Replace S bar? Huh? Okay. S bar goes to reset. Yes, it remains here. Right? 0 1 1 without any condition. It goes to 0 0 1. Right? 0 0 1, correct. 1 0 1, 1 0 0 without any condition, it goes to 0 1 1. 1 0 1, 1 1 0, 1 1 1, not used. You can put don't cares, and all the outputs make 0. So, you can implement it using mux as an example. Use muxes and 3 flip flops, D flip flops and mux solution. The implementation of this mux based solution for this design is shown here. We are using 3 flip flops, D flip flops, with Q's being marked as X, Y, Z. These are the state variables. Dx, dy, dz are the inputs to the D flip flops, all controlled by the clock. Now, each of these Ds comes from 8 to 1 max. For the Dx, X, Y, Z are the selector variables, the state, present state, and the next state information has to be marked here. We know how to do that. We get these values. For example, first input is 0, then it is A bar A 0, 0 0 0 0 0 0, etc. Similarly, for dy, these are the inputs to the multiplexer, 0 A or A 0 bar, S 0 1 0 0 0. For third mux dz, the inputs dz are given by S A bar A 0 bar, 0 1 1 0 0 0. Outputs are very simple. There are only a very few outputs. Load and clear are the same, which are x bar, y bar, z bar, s. Shift A is x bar, y, z. Count B is x, y bar, z bar. So, we have a 3 input solution, three flip flops, each driven by multiplexer whose inputs are connected like this, and outputs can become gotten by simple gates, and we have the entire implementation. With this example, we have seen the system design. We talked about top down design. The approach is to start with a problem, separate the functional unit, which is called the architecture, from the control function, get the functional unit implemented as far as possible from either the components available to you or the IP course, intellectual property course developed by you earlier. You have to be very careful to identify the input output requirements of these functional units. Then go to the state graph of the control state graph of the functional control unit. Let us go through the algorithms systematically and draw the state graph. As we proceed with the state graph, we will find some of the signals not defined properly in the functional units. We might go back and fine tune the architecture, and a couple of iterations back and forth we will have the final the state graph. So, the functional units are already available, the signals we should know how to, what are the control signals available. Of course, the data input and data output are known. In addition, what are the control signals available and how we are going to use them. As far as the controller is concerned, finally it is, turns out to be a state graph, and we know how to implement state graph as shown in this last example. With this lecture, we conclude this course on basic digital system introductory course on digital systems. We have covered a large amount of material in this course. We talked about the digital signals, what is the difference between continuous signals, discrete time signal and digital signals, advantages of processing signals in digital domain, how at the same time we cannot do away with analog signals. So, the real world is analog, both the input and output. So, input signals, analog signals, we do minimum amount of signal processing in analog domain, convert them into digital signals by a process called analog to digital converter, and then go through the digital domain. It can be a simple circuit, the gate, simple combination logic, a simple sequential logic, or some sort of a combinational sequential logic combination we have seen, or some of the systems we talked about, or it could be much more than that. Finally, the output will be digital signals, and digital signals, if they have to drive analog world, you have to again convert them back into analog signals by operation called digital to analog converters. So, we have analog world, analog digital converter, digital processing, digital output, digital to analog converter, convert the signal back to analog into the real world. We have seen the basic building blocks, started with the gates, different types of gates, primary gates, secondary gates, universal gates. We talked about logic functions, how to build simple logic functions using gates. We talked about truth tables, min terms, max terms, sum of products, product of sum. We talked about Boolean algebra for simplification of logic functions, so that we can save on the number of gates used, and we talked about Karnaugh maps. And then we designed some simple combinational circuits functionally, like adders, code converters, maybe parity checkers or parity generators. Then we defined the sequence circuit, the difference between sequential and combinational circuits. Sequence circuit is a circuit in which there is a storage element, memory, which is required in any real time system, any real life system. Then the basic building block of latches leading to flip flops, talked about different types of flip flops, different types of triggering mechanism, master slave and edge triggered. Using building block, the flip flops as building blocks, we talked about counters, registers, shift registers, and simple sequential circuits. When you say sequential circuit, it is not necessarily only the sequential building blocks like flip flops and counters, can also have a driving combination logic. The total system is sequential. That means you have a sequential system which goes from sequence, you have a sequence of states, but when it goes through that, it will be driven by a combination logic. So, the steering logic is combinational. So, the integrated circuit, the total circuit is a combinational sequential combination. And then we talked about instead of going through gate solutions or simple building block solutions, we can go to higher levels of integration. We talked about integrated circuit evolution from small scale integrated circuits to medium scale to large scale to very large scale integrated circuits. So, we talked about MSI and SSI, LSI components for combinational and sequential logic. We talked about multiplexers, decoders, we talked about PROMs, programmable logic devices, programmable logic arrays, programmable array logic, and also how to use this in digital design, either for combinational design or use in steering logic of sequential circuits. And we also said we can also do a similar job with the sequence circuits. Instead of using flip flops, we can use registers and counters to design sequential circuits and steer them using combinational building blocks. Ultimately, we can have a single IC, a programmable logic device, which has both combinational and sequential components in it to implement simple digital systems. And then we took examples of simple code pattern generators. I mean, how to identify the pattern, identification of a pattern from a series of bits, sequence detectors as they are called. Then we talked about other systems, slightly more involved systems like a traffic light controller. We reduced the problem to a state graph and how to do a state graph implementation using different types of approaches, multiplexer base, PLA base, PAL base, PLA base, and also using registers and counters instead of only flip flops for sequential building blocks. And then we got to the concept of top down design, because in the real world somebody gives you a system specification, it does not bother, it does not tell you how to do it, you have to do it the most efficient way. So, best thing is to partition the problem, look at the problem as functional units and control functions. The functional unit is already done, it is available, there is no point in repeating it, no point in designing it over again, no point in reinventing the wheel. Choose these functional blocks, identify the input output requirements and availability, and do the control function alone. So, it is a question of drawing the state graph properly of the control unit. It is a question of identifying the functional blocks along with the input output signals, drawing a sequential circuit control unit, state graph of a control unit, taking into account all the input signals and output signals which will control the sequential building blocks, the functional blocks, and then we have to integrate between these two by means of signals called command signals and status signals. And once you know that, the main job of design is the understanding the problem in its entirety, completely understand the problem, exact specifications as required by the user, the client. As a designer, you should be able to give an unambiguous solution. So, interpreting the specifications properly and drawing the state graph is the most critical part of a digital design. And in the case of an integrated system, in addition to that, to identify the proper functional units, the most efficient way. Having done that, we have the rest of the tools are straightforward. We know how to implement a Boolean function in gate form, in mux form, in PAL form. We know how to draw a state graph, we know how to implement the state graph using different types of logic. So, all these are standard procedures. Of course, you need to do that, you have to reliably build the circuit, test it and make it work. These are non-trivial operations, but still the most important aspect of the design is the identification of the problem, identifying the specifications completely, understanding the specifications completely, and identifying the input signals, output signals, identifying the suitable functional blocks if they are available, or design them using the functional building blocks, basic building blocks, and then identifying and coming up with a state graph and the steering logic and implement the state graph using steering logic. And we have not seen some of those things like how to, we have used arbitrary assignment of states, always sequential, binary sequential. Sometimes there are some guidelines we followed in order to reduce the number of gates required, hardware required. Likewise, we have not done a state reduction. We have given a state graph, we have evolved a state graph. What if there are more states than required? There are procedures. These are trivial things, you can always learn these things. So, in this course we have seen an entirety of starting from the basics of almost from the definition, what is a digital system, what are the various functional units, what are the building blocks, what do you mean by combination logic, what is meant by sequential logic, what is meant by systems, all that. We have seen that to the entire up to designing of simple systems. Of course, I don't, when I say simple system, it is only because of the limitation of time and limitation of the amount of material can be transferred in a classroom. A more complex system or more extensive, I won't even say complex, more extensive system is not all that difficult. All you have to do is to do more of it, which means it takes more time, it takes more sort of more organized work, which cannot be done in a 1 hour lecture in the classroom. But you can easily pick up, the concepts are not going to be very different, concepts are same. We have learned all the concepts required, and of course if we go to very large scale integrated circuits like computers and microprocessor design and digital signal processor design of all these very sophisticated digital systems, you may have to go for other tools, analysis tools, but design tools, synthesis tools. But otherwise, however complex the system may be for a given application, we have the wherewithal to design it and to implement it using the type of components we are asked to design with. So, what is left? Lot more, of course, there is nothing like we have learned all. Basics are clear and we have the capability to design simple circuits. When I say simple, again, it is not simple in the sense of there are more advanced concepts which have not been told to you, it is not in that sense I am saying simple. Circuits are small because we are handling them in a reasonable level of complexity in a classroom. More extensive circuits should try for practice. Certain aspects we have not covered, as I said, the reduction of the states, number of states, assignment of states, assigning binary values for states, so that using some guidelines to reduce the number of gates or the hardware. These are some of the things you can learn by yourself. But one important aspect of a digital system we have not covered is what is known as asynchronous sequence circuits. A circuit can be a combination circuit or a sequential circuit. A sequential circuit goes through states, various states, and the behavior of the present state depends on the present state input and the past output. Now, if it is all done with reference to a clock cycle, we have a clock period as the clock as the basic driving force. With that clock, if you are talking about, then it becomes a synchronous sequence circuit. So, something happens in between clock will not be recognized until the next clock pulse occurs. Mostly it is edge triggered, from this edge to next edge something has to wait. Supposing we are interested in getting things over as fast as possible, a clock is supplied, there is no clock of course in this case, there is a circuit here and something happens, and once that is completed you want to take the next step. But it is not a combinational sense, it is a sequential circuit, but we do not have to be controlled by a clock. Such a circuit is called asynchronous sequence circuit. Asynchronous sequence circuit has the advantage that we do not have to wait for a clock period to be over before we can take the next step. Once the step is completed, the next step can be taken, but that requires a little more analysis, little more detailed analysis and design, just slightly more complex in terms of concepts also. So, that is one thing we have not learned. Otherwise, we are now fairly comfortable with the type of designs which you normally encounter in digital world, and most of the circuits by the way are synchronous sequence circuits. Asynchronous sequence circuits are very few, used only extremely rare cases when the speed is of essence or there are other reasons for going for asynchronous sequence circuits. Barring that, we are having the basic tools required for designing, understanding, analyzing and designing digital circuits, simple digital subsystems, digital subsystem and simple digital systems, and you can very easily extend these concepts to design bigger and larger systems without having to learn any extra concepts. More practice, more examples, more training. So, finally, to summarize this course, we are in the digital world today. Everything is digital around you. Your television is digital, your controller is digital, traffic controller is digital, your washing machine is a digital controller, remote control is a digital control. So, we are talking of digital today in the world, and then we are in this real world. Analog cannot be dispensed with, but we reduce the analog signal processing to the minimum possible extent. So, what are the issues involved here? The issues are how bigger and bigger circuits, larger and larger circuits with the minimum amount of cost. That means we will have to put a lot of functions in a simple circuit. Cost reduction, size reduction, power reduction, performance improvement, speed. Highest performance possible in terms of speed and other quality of performance. At the lowest cost, the smallest area, and that is the world to which we are moving. And you have taken a first step, is a very, very firm first step. It is not a very trivial or shaky step. So, if you have really gone through this material completely and understood all these lectures, the concepts, and worked out the unfinished examples in the class, you are ready for the design to get into the real world, to digital system design. And exercises are not many exercises were given left out in the middle, and I asked you to complete them. Other than that, if you want more exercises, all you have to do is to take a standard book. Of course, I have given a reference book in the beginning. There are this digital system has so many books today. Take any standard textbook on digital system design and then work out the problems, back of the book problems. These are the exercises. There is no need for me to give separate exercises, because there are at least half a dozen good books on basic digital design today. You can take any one of them and then start working out the problems back of the book. Then you will be completely confident of the whole concept, be ready to face the challenge of the real world where we are asked to design complex digital systems. Thank you for listening to this course, and I hope you have benefited by this course.